So let us start. Chemical equilibrium. First, we are going to introduce what do we mean by the equilibrium in nature. The equilibrium in nature may be physically or chemically. So we discuss first the physical equilibrium. Here, the vaporization and the condensation processes explain the physical equilibrium as example. Here, we make an experiment to explain this vaporization and condensation as equilibrium or physical equilibrium. If water is placed in closed vessel and heated, we notice that two processes opposite to each other occur, vaporization and condensation. As shown on the screen, if you bring a conical flask containing water and you are going to start heat it, the vapor increases inside the container and so the vapor pressure increases. So we have a definition here. What do we mean by vapor pressure? It is the pressure due to water vapor in air at certain temperature. As shown on the screen, as the water is heated, the water molecules changes from the liquid state to the gaseous state and move up in the air or the spaces in the flask, so it causes the vapor pressure. Then, if you are going to continue heat, the vapor pressure equals the saturated water vapor pressure. So we have a definition here. What do we mean by saturated water vapor pressure? It is the maximum water vapor pressure in air at certain temperature. So at equilibrium, by continuing the heating the water in the flask, we find that the rate of vaporization equals the rate of condensation. As shown on the screen, this explains the process that happens at equilibrium. The water, by evaporation, it changes to water vapor, and then water vapor condenses to form water, till the amount here of the water vapor in the air reaches maximum that we call saturated water vapor pressure. My dear student, the type of equilibrium in the previous experiment is known as equilibrium system. So, what do we mean by equilibrium system? It is apparently stationary system, but in reality dynamic. There is continuous change occur, but the total amount remains constant. Now, my dear students, we are going to discuss the chemical equilibrium. First, we have to know the types of chemical reaction. We have complete reaction or irreversible chemical reaction. This reaction occurs in one direction only, which means in the direction of formation of products only. So we have division in this point. Complete or irreversible chemical reaction occurs in the direction of formation of products only. We have to say because one of the products escapes from the medium of the reaction in form of gas or precipitate. That's why the products cannot combine with each other to reform the reactants. For example, when reaction of iron with dilute hydrochloric acid, it gives iron to chloride and hydrogen gas. So the hydrogen gas escapes from the medium of the reaction, so the reaction moves in one direction only, which forms the products. Another example, when reaction of sodium chloride with silver nitrate, it gives white precipitate of silver chloride and sodium nitrate solution is formed. Here, the reaction always moves in forward direction only because the formation of the precipitate, that means that escape from the medium of the reaction. The second type of the chemical reactions are the incomplete or reversible chemical reactions. In this reaction, it is the reaction occurs in both forward and backward direction. It means it occurs in the two directions, forward direction forming products and backward direction forming the reactants again. So we have give reason in this point. Incomplete or reversible chemical reaction occurs in two directions. We have to say because both of the reactants and the products are found in the medium of the reaction. That's why the products can combine with each other to reform the reactants again. For example, the reaction of acetic acid with ethyl alcohol as shown on the screen, this reaction is reversible. It forms ethyl acetate ester and water. And so, both of acetic acid and the ethyl alcohol exist in the reaction medium all the time of the reaction, because the reactants form the products and the product reform the reactants again. So we have give reason in this point. The blue litmus paper turns red when it is placed in a container contains 1 mole of ethanol and 1 mole of acetic acid, although the products are neutral. We have to say because the reaction is reversible and the acetic acid exists in the medium of the reaction, so turns litmus red. So the equation as shown on the screen, acetic acid plus ethyl alcohol CH3COOH plus C2H5OH gives CH3COOC2H5, which is ethyl acetate ester, and water is produced. Now, my dear students, so the chemical equilibrium can be defined as it is the dynamic system that takes place when the rate of forward reaction equals the rate of backward reaction. So during this chemical equilibrium, the equilibrium state is reached and it is a stationary system apparently but dynamic in reality. And also, all the reacts and the products are still found in the medium of the reaction. And also, the concentration of reactants and the products are not changed. And also, the condition of the reactions, such as temperature and pressure, are not changed. And also, we find the state of equilibrium may be reached slowly or rapidly. So, my dear students, we can compare between the complete or irreversible reaction and incomplete, which is reversible reaction, as following. The complete reaction, it occurs in one direction only, while in the incomplete reaction, it occurs in forward and backward direction. In complete reactions, some of the products escape from the medium of the reaction in form of gas or precipitate, while in the incomplete reactions, the reactants and the products are still found in the medium of the reaction. And in the complete reaction, the products cannot combine with each other to reform reactants, while in the incomplete reactions, the products can combine with each other to reform reactants again. The example for the complete reaction is the reaction between iron and dilute hydrochloric acid, forming iron 2 chloride and evolving hydrogen gas. Here, the example for incomplete reaction is the reaction of acetic acid with ethanol, giving ethyl acetate ester, and water is produced. My dear student, if the complete reaction gives gases and this occurs in a closed container, it will not be complete reaction. It will be incomplete reaction. My dear students, we have to define what do we mean by the chemical reaction rate or rate of chemical reaction. It is the rate of the change in concentration of reactants or products per unit time. So during the complete reaction, my dear student, the concentration of reactant decreases and the concentration of product increases, as shown in the graph that is found on the screen. While during the incomplete reaction, before the equilibrium has reached, the concentration of reactant decreases and the concentration of product increases, as shown on the screen in the graph. While during the incomplete reaction at equilibrium, the concentration of reactants and concentration of product reaches constant value, as shown in the graph shown on the screen. Now, my dear students, we are going to discuss the factors that affect the rate of chemical reaction. There are 6 factors. Number 1, nature of reactants. Number 2, concentration of reactants. Number 3, temperature of reaction. Number 4, pressure. And 5, catalyst. And last one is light. We are going to discuss each factor in details. We are going to discuss first the nature of the reactants. The first point in this factor is the type of bond in the molecules of the reactants. Ionic compounds react instantly and very fast. So we have good reason in this point. Because the reaction takes place between ions which combine with each other instantly when they are mixed together. As shown on the screen, the equation of reaction of sodium chloride solution with silver nitrate solution giving sodium nitrate solution and wide precipitate of silver chloride. My dear student, the covalent compounds usually react slowly, and we have good reason in this point. Because the reaction occurs between molecules which require breaking bonds between atoms of molecules of reactants, then atoms combine to form new bonds between the atoms of molecules of products. The second point in the nature of reactant is the surface area of the reactants. When the surface area of reactants increases, the rate of chemical reaction increases. So we have to show an experiment to illustrate this point. The steps of the experiment: if we put 2 equal masses of zinc in 2 test tubes, one contains zinc powder and the other contains block of zinc, then add 2 equal amounts of dilute hydrochloric acid on them. What do you observe, my dear student? The reaction goes faster in the test tube which contains zinc powder, while the other tube the reaction moves slow. That means a slower reaction takes place. So the reaction is fast and takes short time in the using zinc powder, while the reaction takes long time when using the block of zinc. So we have good reason in this point, because the surface area in the case of zinc powder is greater than that of zinc block. Now, my dear students, we are going to discuss the second factor that affect the rate of chemical reaction, which is the concentration of reactants. The chemical reaction takes place through collision between molecules of reactants till breaking bonds between the atoms of molecule of reactants. Then these atoms combine to form new bonds between the atoms of molecules of products. So, when the concentration of the reactants increase, the rate of chemical reaction increase. And so we have good reason for this point. Because increasing the concentration of reactants make to increase the chance for collisions of molecules per unit time, which increase the rate of chemical reaction. Now, my dear student, we are going to discuss the law of mass action. The Norwegian scientists Wag and Goldberg established a law which controls the relation between the rate of chemical reaction and concentration of the reactants. And it states that at constant temperature, the rate of chemical reaction is directly proportional to the products of multiplication of the reactant concentration. Each is raised to the power of the number of molecules or ions in the balanced chemical equation. In the following reaction, my dear student, to show the law of mass action between the substances capital letters A, B, C, D and their coefficient, which is a balanced equation for this reaction, A, B, C, D small letters, where A, B, C, D capital letters are the substances present in the reaction, and A, B, C, D small letters are the number of moles in this substance, which is in the balanced chemical equation, and the reaction is at equilibrium state. My dear student, notice that the concentration of reactants and the products is expressed by the formula of the compound or the substance in square bracket. So, for the reactions that we explained before, the rate of forward reaction R1 equal, or we can say the rate of forward reaction is directly proportional to the concentration of the reactant A, capital letter, and the concentration of reactant B, capital letter. And so, the rate of forward reaction R1 equal K1 times concentration of the substance A and concentration of substance B, each is raised to the power of the number of moles in the balanced equation, where K1 here is the rate constant for the forward reaction. So, the rate of the backward reaction R2 is directly proportional to the product of the multiplication of the concentration of the two substances C and D capital letters. Each is raised to the power of the number of moles in the balanced chemical equation. So, R2 equal K2 times the concentration of C and D. Each is raised to the power of the number of moles in the balanced chemical equation. Here, K2 express the rate constant for the backward direction. So, at equilibrium state, the rate of forward reaction R1 equals the rate of backward reaction R2. So, K1 times concentration of substance A and substance B, each is raised to the power of the number of moles, equal K2 times the concentration of the product, each is raised to the power of number of their moles. So, by getting the constants in one side and the concentration in the other side, we have reached to the following relation: K1 over K2 equal concentration of substance C and D, each is raised to the power of number of their moles in the balanced equation, over the concentration of the substance A and B, each is raised to the power of number of their mole in the balanced chemical equation. We can say, my dear students, the ratio K1 and K2 is called the equilibrium constant, and we express it by symbol Kc. The equilibrium constant Kc can be defined as it is the ratio between the rate constant for the forward reaction and the rate constant for the backward reaction. This depending on the concentration of the reactants and products. So we can say Kc equal concentration of substance C and D, which are the products. Each is raised to the power of the number of their moles in the balanced equation, over the concentration of the substance A and B, which are the reactants. Each is raised to the power of the number of moles in their balanced equation. So, my dear students, here we have two cases. If Kc is greater than 1, that means the equilibrium is shifted to the forward direction. That means that the concentration of products are greater than the concentrations of the reactants. But if Kc is less than 1, means the equilibrium is shifted to the backward reaction. So, the concentration of products is less than the concentration of the reactants. So, we have given reason in this point, my dear students. The concentration of liquid water or pure solids or precipitates is not written in the equilibrium constant equation. The reason for that, because their concentrations remain constant whatever their quantity present. Now, my dear students, we have to show an experiment to explain this law. On adding solution of iron 3 chloride that has faint yellow color to ammonium thiocyanate solution, which is colorless, the solution becomes a blood red color. So, we have given reason for this point. The red color is due to the formation of iron 3 thiocyanate, which has blood red color. As the equation proceeds on the screen, iron 3 chloride solution reacts with ammonium thiocyanate solution, forming iron 3 thiocyanate, and ammonium chloride is formed. My dear student, in the forward direction, the rate of forward reaction is directly proportional to the concentration of iron 3 chloride and the ammonium thiocyanate raised to the power of number 3. So R1 equal K1 times the concentration of FeCl3 times the concentration of ammonium thiocyanate power 3, where K1 is the rate constant for the forward reaction, while in the backward reaction, rate 2 R2 directly proportional to the concentration of the product iron 3 thiocyanate and ammonium chloride raised to the power number 3, which is the number of the balanced equation of the reaction. So R2 equal K2 times the concentration of iron 3 thiocyanate and the ammonium chloride concentration raised to power number 3, where K2 here is the rate constant for the backward reaction. So at equilibrium state, the rate of forward reaction equals the rate of backward reaction. So K1 times the concentration of iron 3 chloride times the concentration of ammonium thiocyanate power 3 equal K2 times concentration of iron 3 thiocyanate and the concentration of ammonium chloride raised to power number 3. So at equilibrium state, K1 over K2 equal the concentration of the products, which are iron 3 thiocyanate and ammonium chloride raised to the power of 3, over the concentration of the reactants, which are iron 3 chloride and ammonium thiocyanate. So Kc equals the concentration of the products over the concentration of the reactant, and each is raised to the power of the number of moles in their balanced equation. My dear students, we are going to discuss some examples. The first example here, write the equilibrium constant Kc for each of the following reactions. Carbon monoxide reacts with water, giving carbon dioxide gas and hydrogen gas. The equation for the second reaction, nitric oxide gas reacts with oxygen gas, forming nitrogen dioxide gas. And the third equation, ammonia gas reacts with oxygen gas, forming nitrogen gas, and water vapor is produced. Here, my dear student, the solution, Kc for the first equation, the concentration of carbon dioxide times concentration of hydrogen, which are the products, over the concentration of carbon monoxide. Water is not written as it is in liquid state. And in the second equation, the concentration of nitrogen dioxide gas power 2, which is the number of the balanced equation, over the concentration of nitric oxide power 2 and the concentration of oxygen. While the third equation, the concentration of nitrogen times the concentration of water vapor. Here water is in gaseous state, and so we have to write its concentration in the equation of the equilibrium constant, while the water, which is liquid state, is not written in the equation of the equilibrium constant Kc. Here over the ammonia, power is balance of the chemical equation of the ammonia gas, and oxygen power of 3. Another example, my dear students. Calculate the equilibrium constant for the reaction hydrogen plus iodine gives hydrogen iodide. Given that at equilibrium, the concentration of iodine and the hydrogen iodide are 0.221, 0.221 also, and 1.563 molar respectively. The solution of the problem, we have to write the equilibrium constant Kc equation, which products concentration over reactant concentration. So Hi power 2, because 2 is the number of the balanced equation of hydrogen iodide, over the concentration of hydrogen times concentration of iodine. So we substitute their values of concentration in this equilibrium constant Kc as shown on the screen. So 1.563 power 2 over 0.221 times 0.221 equals 50. Another example, my dear students. Calculate the equilibrium constant for the following reaction. Nitrogen plus oxygen gives nitric oxide gas. Here, the equilibrium concentration of nitrogen gas equals 0.1 molar and oxygen gas 0.1 molar and nitric oxide equals 0.2 molar. Here the solution, Kc equal the concentration of nitric oxide power 2 over the concentration of nitrogen times concentration of oxygen. So equal 0.2 power 2 over 0.1 times 0.1. So equal 4. My dear students, we have reached to the end of our program today. I hope you understood the points that we discussed today and different types of problems. So till we meet again, my best wishes for you.